Welcome to the Drowsy Astronaut. I'm so glad you're here, wherever you are, ready to let go and drift among quiet stars. Maybe it's been a long day, or maybe you just like to fall asleep thinking about galaxies, their calm motion, their endless stillness, the beauty of distance. Either way, tonight's journey is for you, a gentle path through facts and wonder, where the universe itself becomes the background rhythm to your rest. There's nothing you need to do now. Just breathe, slow and easy, and let each word carry you closer to calm. Because tonight, we're exploring the universe itself, not one star or cluster, but the vast whole that stretches quietly in every direction. Now, before we begin, do me a small favor. Let me know where you're tuning in from tonight. It's always a quiet joy to see how many of you join from every corner of the world. And as always, this isn't a lesson to memorize. Think of it instead as a gentle walk with structure, each idea placed carefully beside an image in your mind, moving forward slowly, unhurried, like the universe itself. Some things may surprise you, others may stay with you like a quiet thought, something you'll recall faintly as you fall asleep again another night. And if these moments bring you peace, know you're part of a small constellation of listeners everywhere, finding rest beneath the same sky. The universe might be older than we thought. Current estimates place its age at about 13.8 billion years, measured by faint radiation still echoing across time. That light, called the cosmic microwave background, travels endlessly through space, carrying the memory of its birth through a universe still stretching outward. Astronomers use this signal to trace the story of expansion. Yet even these precise numbers leave small questions, quiet uncertainties, waiting between the stars. Some measurements hint the cosmos could be older by 1 billion years or more, whispering of beginnings we haven't yet understood. If the universe is older, it would change our picture of time, rewriting how stars, galaxies, and black holes formed in the first cosmic dawn. Some scientists wonder if dark energy is shifting with age, stretching or slowing the expansion like breath-changing rhythm in deep sleep. The difference between theories is small but profound, each possibility pointing toward a stranger, longer story than we first believed. And so the question remains quietly open, suspended like dust, glinting softly in a beam of cosmic light. There are planets without stars drifting alone through the void, each a wanderer cast away from its home by gravity's slow violence. These rogue worlds float silently between constellations, unseen but real, their surfaces frozen and dark except for the faint heat they hold within. Astronomers believe there may be billions in our galaxy, more than the number of suns shining in the Milky Way. Each one spins endlessly through blackness. A world with no sunrise, no horizon, no voice but the hum of cosmic radiation. Some of these planets may hide oceans beneath ice, heated by trapped energy that never reaches their skies. If we could stand there, we might see only starlight, faint, distant, a reminder that even isolation can hold beauty. The silence of such worlds is immense, deeper than any cave, heavier than any shadow, filled only with unseen motion. Still, each planet remains part of the same fabric, woven into gravity's web, linked invisibly to every shining star. The universe may recycle itself through infinite cycles, expanding and collapsing, breathing in and out across impossible spans of time. Our current models show expansion continuing forever. Yet some theories describe a gentle return, a cosmic heartbeat, restarting again and again. Each cycle would erase what came before, compressing all stars, dust, and light back into a single point of creation. If that's true, then everything we see, every galaxy, might have existed before in another version of this endless story. Between one expansion and the next, matter reshapes itself, the same atoms becoming new suns, new planets, new forms of life waiting to awaken. Even our own bodies contain particles forged long ago, during earlier cycles when the cosmos was hotter, denser, and still finding balance. To think the universe restarts without memory or name, each rebirth erasing time yet preserving its rhythm, is strangely comforting. It means nothing is ever truly lost, only changed, waiting quietly for its next beginning. There are black holes so massive they anchor galaxies, invisible centers around which billions of stars orbit. They form when great suns collapse under their own weight, pulling everything inward past the point where even light cannot escape. To fall toward a black hole would be to fall without end, your clock slowing as gravity stretches both space and time. Yet from afar, it appears silent and still, a shadow on space itself, marking where the universe hides its deepest secrets. In some regions, giant black holes merge with others, their collision rippling through the cosmos as waves in space-time, too faint to feel, yet vast beyond measure. We've heard those ripples through delicate instruments on Earth, proof that what happens billions of light years away still touches us here. The sound of those waves isn't sound at all, but the bending of the very fabric through which everything moves. Each detection reminds us that gravity connects every particle, no matter how far apart they seem. The light we see from distant galaxies began its journey long before our planet formed, and it continues still, passing us by into the unknown. Every photon travels straight and patient, crossing empty distances so wide that even imagination struggles to follow. When we observe those ancient rays, we see the past. Snapshots of stars as they once were, frozen in cosmic memory. Each glimpse backward stretches our understanding of time and brings a quiet sense of belonging to something larger than life. Scientists suspect there are more galaxies than grains of sand on every beach of Earth, each one filled with its own billions of suns. Beyond what we can see lies more that we can only guess. A horizon not of distance, but of knowledge. Our telescopes collect these faint traces of light, revealing structures so vast they defy every scale we know. And somewhere beyond our reach, the universe continues building, silent, slow, and beautifully indifferent to whether we ever find its end. The facts themselves are enough for wonder, numbers that feel less like mathematics and more like quiet poetry written by nature. Each equation hides stories of creation and decay, of stars living, dying, and giving their matter to the next generation. We study these patterns not only to understand, but to connect, to find our own place in the system we belong to. And every question we answer opens another door, reminding us that knowledge itself is infinite, always beginning again. The universe continues to expand, silent but sure, the fabric of space stretching between every cluster of galaxies. Someday those clusters will drift beyond our sight, their light red-shifted into invisibility as darkness fills the gaps between. Yet even then, the echo of creation will remain, a faint warmth in the background of all existence. And we, made of atoms born in stars, will keep listening to that soft radiation, the oldest lullaby in the cosmos. As you breathe, remember that every atom in your body was once part of a star, burning, collapsing, and reborn across eons. The calm you feel now is not separate from the universe. It is the same stillness that follows every supernova's final breath. When you sleep, the cosmos continues its motion, turning without haste, without concern, endlessly balancing creation and loss. So rest easy beneath invisible constellations, and know that you are made of the same quiet light that fills the universe. The universe continues to expand quietly, stretching its fabric through dimensions we can barely measure. Every galaxy drifts farther, carried by the steady momentum of ancient creation. This cosmic expansion does not mean movement through space, but the growth of space itself. New distance appearing between all things endlessly. If you could watch from outside, there'd be no center, no edge, just uniform motion woven into the background of time. And even as everything separates, gravity holds local families together, galaxies and clusters keeping their quiet companionship amid the drift. The microwave background still hums softly through every direction of the sky, faint radiation left from when light first escaped its foggy prison. It is a message from the moment transparency began, a whisper from the universe's childhood, still arriving 13 billion years later. Every photon carries a story of heat and density, its journey unbroken, slowed only by expansion stretching its wavelength to gentler tones. That glow surrounds you even now, unseen but constant, a reminder that you live inside an ancient afterglow of birth. Somewhere beyond that gentle light, dark matter builds the hidden scaffolding of galaxies, invisible but essential to cosmic shape. We cannot see it directly, yet we know it's there from its gravity bending and guiding the luminous. Through simulations, astronomers map its patterns, filaments and nodes forming a cosmic web where galaxies collect like dew. Without it, no structure could persist. The order we observe would dissolve into chaos long ago. And as we follow that unseen framework, we find great clusters where thousands of galaxies reside, each one a realm of billions of suns. Within those clusters, gravity sculpts graceful arcs of light, distant galaxies distorted into mirrored shapes by gravitational lensing. Such vistas remind us that the laws of physics reach across all scales, uniting tiny atoms and vast superclusters in one set of rules. When you rest beneath the night's silence, you're lying inside those same equations, wrapped by principles that never sleep. The slow birth of new stars continues everywhere, even now, in dark nebulae where starlight barely glimmers through drifting dust. Within those clouds, molecules assemble and collide. Pressure builds until atoms ignite and fusion's first fire begins. Each newborn sun blows a bubble in its cradle. The expanding gas clears, a window into the glow of its nursery. From these regions, light escapes for the first time, and the surrounding void gains another point of brightness. Over time, those stars mature and share their materials. When fusion ends, they scatter the heavy elements forged in their hearts. This cycle of death and rebirth keeps chemistry alive. The next generation of worlds inherits everything that came before. Carbon, oxygen, iron, all were born in earlier stars. Each breath you take connects to furnaces long extinguished. And so, in a quiet way, every living being is part of a stellar family, endlessly recycled, endlessly connected. Between those busy nurseries, interstellar space seems empty, but it hums with magnetic fields and faint waves of radiation. Cosmic rays travel through it, colliding with atoms and dust, leaving traces that reveal their violent origins. This invisible traffic fills even the loneliest reaches. The energy of supernovae still spreading centuries after the light fades. What looks like nothing is quietly alive, threaded with electric currents crossing incomprehensible distances. As centuries pass, stars drift across the sky. Constellations themselves slowly change, though our eyes cannot notice. The Big Dipper of future ages will look unfamiliar. Its stars scattered by their own motions through the galaxy. In this slow choreography, patterns we name are temporary. Our perspective freezes them only for a human lifetime. Even the most permanent-seeming arrangement is fleeting. The canvas of heaven redraws itself forever. Far beyond, galaxies collide in vast, slow ballets. Their stars rarely touch, yet gravity weaves them together over millions of years. Streams of gas stretch between merging spirals. Shock fronts trigger new generations of stars within compressed clouds. Eventually, they settle into one larger shape, calmer than before, their combined core glowing brighter with renewed activity. From destruction comes structure, from chaos, order, and the cycle repeats on scales beyond imagining. Among those galaxies, some harbor black holes of staggering mass, millions or billions of suns compressed into singular points. These objects feed on surrounding gas and stars. Their accretion disks blaze with fierce radiation visible across space. Jets of plasma shoot outward from their poles, beams so long that entire galaxies could fit within their span. Yet inside, nothing can escape the horizon's grip. Every particle surrenders its light to gravity's final embrace. And still, not all black holes devour endlessly. Some rest quietly, their hunger satisfied for now. When they sleep, nearby stars continue peacefully, their orbits adjusted slightly by the invisible weight at the center. We owe many cosmic patterns to these giants' control. Even our Milky Way's heart holds one such presence. One day, its slow pulse will flare again, reawakening the halo of dust and gas that waits around it. Moving outward, we find quasars, galactic hearts blazing with intensity. They outshine entire galaxies through the energy of falling matter. They existed mostly in the universe's youth, when fresh gas was abundant and black holes were eager feeders. Each quasar marks a chapter of wild growth, its light crossing billions of years to reach our telescopes. Even after fading, they leave traces in intergalactic gas, invisible signatures showing where ancient power once burned. Between these beacons lie vast voids again, quieter still. Faint galaxies linger like dust motes drifting in morning light. Even there, dark energy presses outward, its mysterious force accelerating the universe's expansion over time. No one knows what causes this acceleration. We only see its effects in redshifts that grow faster with distance. In that mystery lies cosmic humility, a constant reminder that our equations still leave room for wonder. Closer to home, our own sun continues its calm routine, fusion in its core balancing gravity's inward pull perfectly. Every second, it turns mass into pure energy, enough to power civilizations trillions of times over if harnessed directly. Its stability defines life on Earth, a steady pulse that has lasted 4.5 billion years without pause. Someday that balance will end, but not yet. Our moment sits safely between creation and collapse. The sunlight that warms your face began its journey long ago. Photons take thousands of years to reach the surface from the core. Once free, they travel just 8 minutes to Earth, a distance that connects us to fusion's distant heart. Each beam carries a memory of collisions within plasma, its path twisted countless times before escape. By the time it arrives, that light has already lived many lifetimes, a quiet traveler finishing a journey of patience. Planets orbiting other stars reveal immense diversity. Some glow with reflected light from their suns, others with heat from formation. Gas giants closer than Mercury burn red from compression, their skies streaked by metallic clouds and chemical rain. Farther out, frozen worlds drift in cold clarity, their thin atmospheres barely holding a trace of warmth. Each discovery expands the definition of possible planets and the imagination of what might dwell on them. Beyond planets, smaller bodies fill the dark, asteroids, comets, and icy fragments left over from creation. Their collisions shape new surfaces and deliver materials. Even Earth's oceans may have arrived from such wandering messengers. When comets approach the sun, their ices sublimate. Tails of dust and vapor stretch millions of kilometers outward. These glowing arcs are cosmic signatures of impermanence, bright for a moment, fading again into darkness. Meteor showers trace those cometary paths each year, as Earth crosses streams of dust left behind in orbit. The streaks we see are grains no larger than sand. Their flare is air heating as particles vaporize high above. Each meteor burns quickly but beautifully. A small reminder that space and Earth remain in constant contact. Under clear skies, their patterns repeat faithfully. Silent gifts from cosmic debris returning again and again. Even your body's atoms tell the same story, forged in old stars, carried by explosions, and gathered by gravity into flesh and bone. Every breath contains particles once part of mountains and moons. The same hydrogen that fueled early suns flows now through you. The scale may be different, but the process identical. Nature recycles everything, never wasting, never resting. That connection between life and the cosmos endures, unchanged, invisible, and endlessly comforting. Long after sunlight leaves a star, its journey continues endlessly. Photons cross the void, unbothered, slowed only by the stretching of expanding space. Every beam tells us where it came from, its color and faintness revealing the temperature, size, and age of its parent star. By studying those spectra, astronomers can read entire stories. A single line of missing wavelength marks an element forged billions of years ago. It is remarkable that light can be so fragile, yet so truthful, carrying precise memory across impossible distance. And beyond the range of visible light lies a deeper spectrum. Radio, infrared, X-rays, and gamma rays all whisper different secrets of the sky. Some objects emit strongly at one end, faintly at another. Their behavior across the spectrum helps decode what's hidden from normal eyes. Telescopes tuned to radio waves can see cold hydrogen clouds, mapping arms of galaxies invisible through dust, while orbiting observatories catch high-energy flashes, tracing events like black hole mergers and supernova remnants expanding into space. Galactic rotation curves once puzzled scientists. The outer stars moved too fast to be held by visible mass alone. That observation hinted at dark matter long before we could name it. Unseen substance outweighing everything luminous combined. As surveys improved, this invisible mass revealed its structure. Vast halos surrounding galaxies, shaping their long-term stability. Even now, we only measure its gravitational touch. The identity of dark matter remains one of physics' gentlest mysteries. Some galaxies spin like graceful spirals, their arms marked by young blue stars forming in waves of compression. Others appear elliptical, smoother and older, lacking cold gas. They shine with ancient red populations and little new birth. Irregular shapes tell stories of past collisions, disturbed structures left behind when two systems once met. Each type reveals a timeline of evolution, and each difference widens our sense of what galaxies can become. Between those distant islands of matter, filaments stretch for millions of light years. Streams of hydrogen connect clusters like faint threads of glass. Along those pathways, galaxies flow slowly toward common centers, their shared motion showing how gravity sculpts even the largest patterns. Astronomers call this cosmic web the backbone of the universe. Every node a meeting place where dark matter and baryons intertwine. From afar, the geometry looks delicate but vast, its quiet architecture maintaining order over everything we can observe. The Milky Way itself participates in that dance, its spiral arms turning once every few 100 million years. Stars inside orbit at different speeds but stay in step. The wave of density moves faster than any single star can travel. It's like standing in a crowd where motion flows collectively. The pattern remains though the people change. This galactic wave preserves form through rhythm alone, and the harmony continues across billions of cycles. Our galaxy also carries a faint stellar halo. Ancient stars and globular clusters orbiting far beyond the bright disk. These relics hold memories of early formation. Their chemical signatures show that the Milky Way grew by absorbing smaller galaxies. Every captured stream adds a thread to the whole. The trails of those mergers still linger faintly in the night. We live within that mosaic of countless histories. Our sky's quiet pattern is really a fossil of motion and time. Near the center of our galaxy, stars orbit something unseen. Their tight paths betray the presence of a supermassive black hole. This dark core, called Sagittarius A, weighs millions of suns, its gravity binding nearby gas into a swirling disk. Occasionally, it feeds, releasing flares of X-ray light, then settles again into long periods of calm. That sleeping engine reminds us how power and stillness coexist. Immense, yet silent enough to cradle entire systems around it. Farther out, smaller black holes form when massive stars collapse, their remaining mass concentrated so tightly that light cannot escape. Some exist as quiet singularities with no nearby companions. Others pair with stars and draw matter from them. When infall begins, energy erupts in X-rays and jets. Magnetic fields focus the outflow into narrow beams across space. We detect these bursts as short flickers of light, each signal a momentary echo of gravity's deepest pull. Neutron stars sit beside them as dense fragments, just a few miles wide, yet heavier than the sun itself. Within that crushed matter, atoms no longer exist individually. Protons and electrons merge into pure neutrons, bound tightly. Their magnetic fields twist into incredible strength. Beams of radiation sweep the cosmos like cosmic lighthouses. As they rotate, pulsars tick with astonishing precision, natural clocks that measure time far better than our machines. Sometimes two neutron stars collide, merging violently. The resulting explosion releases gravitational waves that ripple across space-time. Those waves stretch and compress everything in their path. Even the most rigid matter moves, though imperceptibly. Observatories like LIGO listen for such signals. The delicate vibrations confirm Einstein's vision of warped geometry. From those collisions, gold and platinum form. The metals we treasure owe their existence to cosmic violence. Across vast epochs, even galaxies merge in similar ways, their halos overlapping and triggering enormous bursts of star formation. Eventually, the cores combine and settle into new balance. One merged system, shining brighter than either alone. The Milky Way and Andromeda are destined for such a meeting. In a few billion years, their disks will intertwine. From that union, a single elliptical galaxy will emerge, its new name written in the stars of both. Some galaxies host glowing jets, thousands of light-years long. They erupt when central black holes accelerate particles near light speed. These streams pierce intergalactic space and light up distant gas. Enormous lobes of radiation trace where energy has traveled. The mechanisms involved remain partly mysterious. Magnetic threads guide plasma with elegance we're still learning to describe. Such scenes remind us that extremes coexist with serenity. Even violent forces can produce enduring beauty. Yet alongside grandeur, tiny particles play essential roles. Atoms and photons together set the rhythm of cosmic temperature. The background radiation still cools as space expands. Its average energy falls in harmony with growth of scale. Astronomers measure this cooling with great precision, each new value fitting perfectly within theoretical expectation. The universe remains predictable despite immensity. Mathematical consistency links the smallest quantum to the grandest void. Closer to the interstellar medium, clouds reveal shifting patterns. Ultraviolet starlight drives subtle chemistry inside their shadows. Complex molecules like formaldehyde and ammonia emerge. Their presence shows that precursors to life exist widely. When these clouds collapse, the molecules survive within disks, embedding their recipes into new planetary systems. Among those systems, binary stars outnumber single ones, two suns orbiting each other in delicate gravitational balance. Their mutual dance creates alternating patterns of light and shadow. Planets there experience twin days and mirrored seasons. Astronomers watch these pairs eclipse and reveal details. The changing brightness allows calculation of mass and size. In the night sky, such duos appear as single points, but their internal motion tells of harmony unseen. When massive clusters form, hot gas fills the spaces between galaxies. This medium glows faintly in X-rays visible to orbiting observatories. Shock waves propagate through it as galaxies move and merge. The resulting ripples heat matter to millions of degrees. This intergalactic plasma outweighs all the stars combined. Its presence confirms that much of cosmic matter hides in gas. What seems like emptiness is actually a sea of energy, still expanding, still responding to gravity's pull. The cosmic microwave background isn't perfectly smooth. Slight fluctuations in temperature mark the seeds of future structure. These patterns record density variations from the earliest moments. Gravitational growth later amplified them into galaxies. Mapping this texture with satellites reveals ancient physics. The differences, only millionths of a degree, tell how matter behaved then. It's astonishing that noise so faint defines everything visible, yet those tiny variations shaped the entire observable universe. Time across the cosmos flows differently depending on gravity. Near massive objects, clocks slow, while distant ones race ahead. Astronauts orbiting Earth age a fraction slower. Though the difference is tiny, it proves relativity's reach into everyday motion. On galactic scales, time dilation becomes dramatic near black holes. The illusion of frozen matter arises from infinite delay. In that sense, observation itself is part of the story. Our measurements influence what we call now and then. At the edge of known space, galaxies recede faster than light, not by motion through space, but because space itself expands beneath them. Their photons stretch into longer wavelengths, losing energy. The deep redshift marks distance like a cosmic clock. Eventually, their light will never reach us again. The horizon of visibility shrinking as expansion accelerates. So every night's view is temporary, each seen object drifting slowly out of reach forever. Even with that fading, the cosmic web endures in its vast quiet. Gravity still binds what expansion cannot unmake. Clusters remain connected by filaments, trading gas and heat. These exchanges sustain galaxies for billions of years to come. Within those filaments, fresh fuel flows into star-forming regions. The stream ensures the universe never truly rests. It is a patient machine that recycles everything, each cycle slower but no less certain. Through all of this, our own existence becomes perspective, a single moment of awareness inside a continuum that rarely notices itself. To look upward is to join that continuum, your mind participating in patterns older than life. Every question asked about the sky adds meaning. Curiosity itself becomes part of cosmic evolution. So as you rest tonight, let thought drift outward, the same gentle motion that governs every star and atom. As we move further into the universe, we find that matter is not evenly spread. Instead, it collects into threads, knots, and spaces shaped by invisible gravity. This uneven structure began from tiny fluctuations in early density. Over billions of years, those faint variations grew into the pattern we now observe. Galaxies trace this cosmic web like dew on invisible strands, each cluster connected through thin bridges of dark matter and gas. When viewed from afar, the pattern appears vast yet delicate, its repeating geometry quietly consistent from one edge of the sky to another. Within those threads, galaxies evolve over unimaginable spans of time, their billions of stars forming, dying, and enriching the gas around them. Some galaxies merge, while others remain solitary for eons. The balance between collision and isolation determines their shapes and brightness. Every galaxy's history is written in light and motion. Astronomers read that history by mapping rotation speeds and colors across the disk. The more we observe, the clearer it becomes that change is the only constant on cosmic scales. There are elliptical galaxies, smooth and featureless in appearance. Their stars are old, red, and settled into quiet stability. They contain little cold gas for new stars to form, so their light fades slowly as their stellar populations age. In contrast, spiral galaxies remain dynamic and rich, their arms filled with glowing hydrogen clouds and regions of recent formation. Both types represent different phases of galactic life, one of activity and one of rest. Beyond the visible lies a class of dwarf galaxies, faint and small. Their few million stars orbiting larger companions as satellites. They are fragile structures, often distorted by tidal forces, their shapes stretched or broken by the gravity of nearby giants. Despite their size, they play an important role in cosmic assembly. Many larger galaxies were built through the merging of smaller ones. In this way, even the faintest systems contribute to growth. No piece of the cosmos is truly insignificant. Between galaxies, hot gas glows softly in X-rays. It fills the space of clusters with temperatures reaching tens of millions of degrees. This intracluster medium carries most of the cluster's mass. Its pressure prevents galaxies from escaping the group's collective gravity. When clusters collide, shock fronts ripple through the gas, producing long arcs of light visible to sensitive instruments. The collisions seem violent but orderly, following the laws of energy transfer that govern even chaos. Over longer timescales, superclusters link together into greater formations, sheets and walls of galaxies that span hundreds of millions of light-years. Between them lie immense voids where few galaxies exist, regions so vast that radio signals travel for ages without echo. Astronomers map these structures with surveys that chart millions of positions. The patterns reveal how matter and energy shape expansion. Even in these scales, the web remains consistent, the same invisible framework repeating at every level. Closer to home, our Milky Way belongs to a group of nearby galaxies, together with Andromeda, Triangulum, and dozens of dwarfs. They orbit a shared center defined by gravity, slowly approaching each other over billions of years. Eventually, Andromeda and the Milky Way will merge, their combined mass forming a single, larger elliptical galaxy. For now, they remain companions, separated by vast distance, connected only by faint streams of hydrogen and dark matter. Inside our galaxy, the disk itself holds remarkable structure. Its spiral arms curve outward from a bright, crowded center. Those arms are not fixed arrangements of stars. They are waves of density that move through the disk like ripples in water. Stars form and fade as the waves pass through. The pattern remains, though the participants constantly change. From our view within one of those arms, we see the Milky Way as a hazy band across the night sky. The center of our galaxy hides a supermassive black hole, its presence revealed by stars orbiting at incredible speeds nearby. This region is crowded with gas and magnetic turbulence, each movement feeding or disturbing the black hole's quiet hunger. Sometimes it releases bursts of high-energy light, moments where surrounding material briefly shines, brighter than the rest of the galaxy. Most of the time it remains calm, patient, and silent, a reminder that immense power can rest in complete stillness. Elsewhere, smaller black holes drift unseen among the stars. They form when massive suns end their lives and collapse inward. Some capture nearby companions and feed on their gas, pulling matter into spirals that glow hot before disappearing. When enough mass falls inward, energy escapes as radiation. The process converts gravitational pull directly into light. Despite their darkness, black holes illuminate their surroundings, their invisible influence shaping entire regions of space. In distant galaxies, powerful jets erupt from active centers, streams of charged particles accelerated to near light speed by magnetic forces. These jets extend for thousands of light years, colliding with intergalactic gas and forming glowing lobes of radio emission. They mark the boundaries where black holes exert influence beyond their immediate vicinity. Even across vast distances, these signals persist, each jet a quiet signature of extreme physics at work. When such activity ceases, galaxies enter quieter phases. Their energy output drops and star formation slows naturally. The dust and gas once used for new stars become thin, leaving populations of older, cooler suns behind. The universe still glows with their faint light, gentle remnants of more active times long gone. In the stillness between generations, matter rests again, waiting for gravity to begin another cycle of creation. Throughout all of this, radiation travels across the cosmic background, every wavelength carrying information from different eras of history. Radio telescopes listen to the longest waves stretched by expansion. Their faint signals preserve the universe's slow cooling. Infrared observations reveal dust and heat invisible to optical eyes, opening windows into star-forming regions hidden within clouds. From radio to gamma rays, the spectrum tells a story. Light itself acts as both messenger and memory. Sometimes a star ends its life in a supernova, an explosive event that scatters heavy elements across space. This material enriches the gas between stars. Future systems inherit it and form planets with metals, water, and carbon. Supernova remnants glow for centuries, their shockwaves expanding, sweeping paths through interstellar clouds. Each explosion is both an ending and a beginning, one more link in the long chain of cosmic recycling. Among these explosions are neutron stars, small and dense. Their gravity compresses matter beyond anything we can reproduce on Earth. Some spin rapidly and emit pulses of radio waves, their timing precise enough to measure gravitational effects elsewhere. Others exist in pairs and eventually merge, creating short bursts of gamma radiation that travel across the universe. Not every star ends violently, smaller ones fade gently, their outer layers drift away, leaving white dwarfs behind. These compact cores shine faintly for billions of years, cooling slowly until they become cold remnants of light. Sometimes two white dwarfs collide, igniting briefly as Type Ia supernovae. The resulting flash helps measure cosmic distance. Even in death, these objects serve science's purpose. Their predictable luminosity acts as a ruler for the expanding universe. Elsewhere, giant planets influence their systems profoundly. Their gravity sculpts the orbits of smaller bodies and debris. Jupiter-like worlds protect inner planets from excess bombardment. Their pull redirects asteroids and comets away from fragile environments. Without such guardians, life might never gain foothold. The early Earth's history benefited from similar cosmic protection. These quiet roles played by gas giants are rarely seen, but their effects shape everything that follows. Among these planets, some worlds orbit so close to their stars that surfaces boil, temperatures high enough to melt rock into vapor. Others exist where rains of iron or glass fall sideways. Winds move faster than sound across their alien skies. Even these extremes are part of cosmic normality. Every configuration permitted by physics eventually exists somewhere. For those who observe from afar, such variety is not chaos. It is simple evidence of abundance. Beyond stars and planets, comets wander in elongated orbits. They carry icy material from the outer reaches of their systems. When they near a star, heat vaporizes their frozen gases. The resulting tails stream outward and reflect sunlight. Each orbit reshapes the comet's core, revealing layers from its formation. For astronomers, these fragments are windows into the early days of solar creation. Asteroids and meteoroids also preserve ancient matter, remnants of construction left over from planetary assembly. Their craters mark impacts that have shaped countless surfaces, each strike adding texture to barren moons and worlds. Occasionally, one visits Earth and survives the atmosphere, fragments of iron and rock revealing chemistry from long before our planet cooled. By studying them, we understand the solar system's past. Every sample a small archive of cosmic memory. The solar wind flows constantly from the sun's outer layers. Its charged particles travel through the solar system at supersonic speeds. When this wind meets magnetic fields, auroras form. Colorful arcs of light shimmer near polar regions of planets. Each display illustrates the invisible connections between star and planet, the interaction that keeps atmospheres dynamic and alive. What appears as beauty is actually magnetism in motion, a process shared by Earth, Jupiter, and many others. Across time, the universe remains stable in its laws. Gravity, electromagnetism, and nuclear forces behaving predictably everywhere. This consistency allows complex systems to exist. The same principles guiding atoms also govern galaxies. No matter where we look, the equations hold, from the smallest particle to the farthest cluster of light. Such reliability may seem simple, but it sustains order in an otherwise infinite landscape. And as you lie here listening, the cosmos carries on, its quiet motion unbroken, its processes steady as ever. From photons to galaxies, everything moves at its appointed pace. each cycle completing itself without hurry. Our awareness is a brief window into that stillness, every thought, every breath part of a larger rhythm. So let the facts settle softly into calm, their gentle truths aligning with the silence around you. Far beyond our Milky Way, the universe continues to expand. Galaxies drift apart slowly, carried by the steady stretching of space itself. This expansion has no center. Every point moves away from every other as though distance itself were being created. Astronomers measure the rate using redshift from distant light. The further a galaxy, the faster it seems to recede. Over billions of years, the pattern stays consistent. Silent proof that space still grows between all things. Some of that expansion is driven by dark energy, an unseen force, its presence detected only by the acceleration of galaxies far apart. No known particle explains it, yet its influence fills most of the cosmos. When cosmologists add up the universe's contents, only a small portion is ordinary matter. The rest remains invisible, its properties still uncertain despite precise observations. Even stranger is dark matter, a substance that adds weight, keeping galaxies bound when they should fly apart. It neither emits nor reflects light, but its gravitational effect is unmistakable. Astronomers trace it through rotation curves of stars in galactic disks. The outer stars move too fast to be explained otherwise. Simulations that include dark matter recreate real structures, confirming its unseen hand in cosmic design. Between stars, dust, and gas fill the interstellar medium, thin as a whisper, yet vital to the creation of new suns. These grains of carbon and silicates absorb ultraviolet light, re-emitting faint infrared glow that telescopes can detect. Each particle drifts for millions of years, joining larger clouds under gravity's pull. From those clouds, stars ignite anew, recycling old matter into bright generations again and again. Within those clouds, protostars begin as small spheres, collapsing under gravity until their cores reach intense heat. Once nuclear fusion begins, a balance forms. The outward pressure of radiation counters the inward pull of collapse. This steady equilibrium marks the true birth of a star. Light now escapes, signaling stability. Different masses create different destinies. Some will burn quickly, others glow softly for trillions of years. The Sun, our familiar star, follows this same pattern. Born from a spinning disk of gas and dust, it consumes about 4 million tons of hydrogen every second, converting it to helium through the fusion process. That energy travels outward over thousands of years before reaching the surface, emerging finally as the sunlight that warms Earth. Even at that scale, the output stays remarkably steady, one of nature's most reliable rhythms. Around young stars, disks of debris spin and flatten, where gravity and collisions sculpt planets from dust. Microscopic grains stick together through electric attraction, slowly growing into pebbles, then rocks, then worlds. Not every fragment survives the chaotic process. Some fall back into the star or drift away into space. But when balance emerges, a new system takes shape. The architecture determined by the original cloud's spin and temperature. Some planets form close, heated and stripped of lighter gases. Others take shape farther out beyond the frost line. Those distant regions allow ice to accumulate, building giant cores that capture massive atmospheres of hydrogen and helium. The results are gas giants, like Jupiter and Saturn, their bulk shaping the orbits of everything else nearby. In each system, similar principles apply, even if the outcomes vary greatly from one star to another. Beyond the outer planets, comets and icy bodies linger, remnants of early solar construction frozen for billions of years. When disturbed by gravity, they plunge inward toward the light, their surfaces releasing vapor that forms long glowing tails. Every return reshapes their composition slightly, a record of both ancient and modern cosmic chemistry. Astronomers use them to trace the early solar conditions, like fossils of planetary formation. Asteroids, meanwhile, are rocky leftovers from the same process, never large enough to form spherical worlds. Many reside in the belt between Mars and Jupiter, where Jupiter's gravity prevented their unification. Collisions among them scatter fragments across the solar system. Some reach Earth as meteorites carrying metals and crystals. Their varied textures preserve early heat and impact histories, giving scientists direct evidence of the solar system's youth. Occasionally, planets exhibit rings made of ice and dust. Saturn's system is by far the most complex. Its rings stretch hundreds of thousands of kilometers, yet remain thin. The particles range from grains to mountain-sized chunks. Light passing through those rings creates bright and dark bands, a pattern influenced by gravity from nearby moons. The beauty we see hides constant motion, collisions, shadows, and slow rearrangement of frozen debris. Saturn's largest moon, Titan, holds a dense atmosphere, thicker than Earth's and rich in methane and nitrogen. There, rain falls, not as water, but as liquid hydrocarbons. Lakes and rivers glimmer under faint sunlight, forming a strange yet stable version of a weather cycle. If ever explored closely, Titan's surface would appear alien yet familiar. A mirror of processes found on Earth but with different ingredients. Another world, Europa, hides an ocean beneath its icy shell, kept liquid by heat from Jupiter's tidal forces. Its smooth surface shows cracks where ice plates drift, letting salts and minerals rise from the depths. Beneath kilometers of frozen crust, that ocean could harbor life, microbial or chemical, powered by energy from vents. Future missions aim to confirm these conditions, probing for signs that biology can exist beyond sunlight. Farther out lies Neptune, deep blue and distant. Its winds are the fastest recorded anywhere in the solar system. The planet's faint rings and strange storms persist, shaped by internal heat more than sunlight. Even farther beyond, Pluto and other dwarf planets continue to orbit, remnants of a wider family of icy bodies. Their varied compositions remind us that planetary diversity extends far past the limits of classical models. Among all this variety, gravity holds everything together. From moons to galaxies, the same law applies. It weakens with distance, yet never disappears. Its reach defines the structure of every celestial system. Einstein showed that gravity bends space itself, and light follows those curves as it travels. This bending allows lensing effects that magnify distant galaxies like natural telescopes. These lenses have become tools for astronomers, letting them see objects too faint or far for direct observation. By measuring distortions, they map the hidden matter behind, turning space into a cosmic laboratory. Sometimes one galaxy acts as a lens for another behind it, producing rings or arcs of multiplied light. Such alignments occur purely by chance, yet they reveal details from epochs near the beginning of time. Stars themselves act as clocks, marking cosmic ages. Their colors and brightnesses record temperature and evolution. Massive stars burn faster, living brief, luminous lives, while small red dwarfs may persist for trillions of years. By comparing populations, scientists estimate the history of galaxies, linking color to age and formation rates. This simple pattern turns scattered points of light into records of change. Some regions of space glow intensely in X-rays, signals from matter heated while falling toward black holes or neutron stars. Such radiation reveals invisible engines of energy, compact objects transforming gravity into heat and light. Orbiting telescopes detect these bursts and trace their origins. Each observation extends our reach beyond visible wavelengths, adding another dimension to our picture of the universe. Even between galaxies, faint radiation still exists, the cosmic microwave background left from the universe's infancy. It provides a precise snapshot of temperature differences across the early sky. Those tiny variations seeded everything we now observe, the evidence measured by satellites over decades. From that pattern, we learn the age, shape, and composition of everything we can see. When we think about cosmic time, human scales become small. Our entire civilization spans only moments compared to stars. A galaxy's rotation takes hundreds of millions of years, yet the laws that move it act continuously. This vast difference gives the cosmos its quiet dignity. Our brief existence happens entirely within an unhurried continuum. Even so, human curiosity bridges the gap between small and infinite. Through instruments, we extend our senses far beyond our planet. Each discovery adds clarity, revealing new mysteries still unsolved. The more we learn, the more questions emerge. This cycle mirrors the expansion itself, endless, calm, and open. Knowledge, like light, travels forward without stopping, reaching whoever chooses to listen. And as this quiet session nears its close, the facts themselves begin to settle into gentle order. You might notice how steady rhythms slow your breath. The mind drifts through space the way dust drifts through light. All that remains is calm awareness. The simple truth that everything continues peacefully and vast. The stars that reach the end of their long lives collapse inward, their cores crushed by gravity until no resistance remains against the pull. In that instant, a supernova releases more energy than billions of suns, scattering elements that will someday build worlds and oceans. The light from such events travels across millions of years, carrying stories of birth and destruction written in invisible waves. Through these distant flares, astronomers trace the path of matter, revealing connections between our atoms and the death of ancient suns. After the chaos fades, the debris from the explosion drifts outward, clouds of gas mixing quietly with colder interstellar dust. Over time, gravity gathers these remnants again, forming new stars from what was once broken apart. Each generation adds layers of chemical richness, shaping planets that inherit the ashes of the old. And so creation and destruction alternate endlessly, their balance maintaining the rhythm of the cosmos. Some remnants collapse even further, becoming neutron stars of impossible density. Their mass packed into spheres no wider than a city. A teaspoon of this matter would outweigh entire mountains, a silent proof of nature's pressure beyond comprehension. These stars spin with incredible precision, their pulses flashing rhythmically across space like cosmic metronomes. Scientists use their steady beats to measure distance, turning light years into predictable intervals of time. For the most massive stars, collapse never stops. Gravity tightens until even light cannot escape. A black hole is left behind, its boundary marking the edge where time and space cease to behave normally. Around it, swirling gas forms a glowing disk, friction heating the material until it shines brighter than a galaxy's heart. As particles spiral closer, their motion slows to an outsider's eye, creating the illusion that time itself stands still. Despite their mystery, black holes obey the same cosmic laws, their pull acting only through gravity's familiar curve. Matter must come close enough to fall inward, otherwise it continues on its path untouched and free. When two black holes merge, ripples spread outward. These waves stretch and squeeze space itself as they travel. Detectors on Earth can sense these distortions, turning silence into measurable proof of gravity's hidden voice. These ripples confirmed Einstein's century-old prediction, showing that space can bend and breathe like an ocean's surface. Each wave carries information about its source, revealing mass, speed and rotation locked within the collision. When analyzed carefully, they unfold the story of unseen events, allowing astronomers to witness what no telescope can show. Through them, the universe reveals its extremes, translating chaos into patterns of energy and motion. Not all remnants end in violence, some fade instead. White dwarfs cooling slowly for trillions of years. Their faint light diminishes with time, becoming invisible to even the most sensitive instruments. Eventually, they solidify into black dwarfs, relics of long-extinguished flames that once fueled stars. These quiet bodies remind us that endings need not burn. They can rest instead in everlasting calm. In systems where stars share gravity, one may steal from another, its pull drawing steady streams of gas across the void. As the gas falls onto its companion, fusion reignites explosively, producing a brief nova visible across distant skies. This outburst fades quickly, returning to peace, the donor star continuing its orbit as though nothing happened. Even in repetition, these quiet bursts sustain balance, a reminder that stability can coexist with eruption. Star clusters reveal groups of siblings formed together, their shared motion carrying them through the galaxy as one. Globular clusters are among the oldest structures known, containing stars nearly as ancient as time itself. Within their dense centers, orbits interlace and evolve, each encounter subtly altering paths over millions of years. Astronomers study their patterns to understand stellar aging, finding harmony inside unimaginable complexity. Elsewhere, vast nebulae span light years of color and dust, the cradles where new stars ignite. Each nebula's shape changes slowly, sculpted by radiation and the winds of young suns. Through telescopes, these clouds appear almost alive, their glowing edges hinting at endless hidden formations. Within them, planets begin to form from simple particles, their growth silent, patient, and unstoppable. The exoplanets we've discovered vary more than anyone imagined, each system presenting a different story of creation. Some worlds circle their stars so closely, the heat would vaporize rock within minutes. Others orbit far away, wrapped in ice and shadow. Between them lie countless possibilities for life, the universe testing every possible combination of matter and distance. Many of these exoplanets are giants, orbiting faster than Mercury, their gravity shaping surrounding systems like cosmic architects. These hot Jupiters are unstable yet enduring, their winds roaring at thousands of kilometers per hour. As they spin, their atmospheres glow under relentless radiation, revealing patterns of heat that defy equilibrium. Each observation helps us understand how such systems evolve, refining our models of distant formation. Between the bright stars of every galaxy, billions of rogue planets drift, untethered, unseen, and alone. These dark worlds were likely ejected by gravity's chaos during their youth. Without sunlight, they radiate only faint internal heat, their hidden oceans sealed beneath frozen crusts. Yet even these orphans carry potential ingredients for life, silent wanderers awaiting a second chance. Beyond the boundaries of any system, brown dwarfs exist as failed stars, their mass too low to sustain true fusion. They glow faintly in infrared wavelengths, detectable only by instruments tuned to warmth rather than light. Their presence bridges the gap between planets and stars, expanding our sense of what lies between. Each discovery adds clarity to our definition of creation's diversity. In galaxy cores, supermassive black holes anchor entire structures, their gravitational pull shaping millions of orbits. Around them, jets of plasma erupt outward, powered by magnetic fields that thread through the accretion disk. These jets stretch for light years through space, broadcasting energy across radio and X-ray bands. Despite their violence, these centers remain stable, maintaining order amid chaos on unimaginable scales. Galaxies collide more often than they destroy, their motions guided by gravity's patience rather than chaos. When they meet, stars rarely crash. The spaces between them vast enough for safety. Instead, clouds compress, igniting waves of new star formation. From apparent destruction, beauty emerges, spirals merging into elliptical shapes that will last eons. Our own Milky Way is on a slow collision path with Andromeda, its approach steady and predictable. In 4 billion years, the two will merge into a single, massive system. No individual star will strike another, but gravitational tides will reshape their orbits forever. Future skies will glow with double constellations, remnants of galaxies that once watched each other from afar. Superclusters hold thousands of galaxies connected through invisible filaments, the universe's largest known architecture. Between them stretch voids, nearly empty, regions where only hydrogen's faint whispers remain. This web of structure reflects early fluctuations in the cosmic microwave background. Through it, astronomers can trace evolution from the first moments of expansion to now. Mapping this web requires surveys of deep space and precision instruments. Redshift data reveals how fast galaxies recede, each measurement refining our sense of the universe's scale. Simulations model billions of particles, showing how gravity's laws sculpt vast structures over time. When compared to observation, these maps align perfectly, confirming the patterns predicted by theory. Within our own galactic neighborhood, the Sun drifts through a bubble cleared by ancient explosions. This local region extends for hundreds of light years, filled with warm gas thinner than vacuum itself. The Sun moves gently through it at 20 kilometers per second, carrying all its planets along the same path. It is a small but peaceful pocket of space, evidence that even chaos creates refuge. At the edge of our solar system, the heliosphere shields us from interstellar radiation. Its border lies far beyond Pluto, where solar winds slow and mix with alien particles. Voyager probes have crossed this frontier, their faint signals still whispering across the darkness. They remain our farthest messengers, silent and steady in their journey beyond the Sun's reach. Each golden record aboard them carries music and images from Earth, a hopeful message to whatever may listen. Somewhere beyond our perception, those records float endlessly, bearing the essence of a curious species. If ever found, they would speak of oceans, laughter, and time. Fragments of home carried through cosmic silence. Their existence reminds us that curiosity is eternal, and our story continues wherever light can reach. The galaxies we see today are only one moment in their story. Each collection of stars has changed, merged, or drifted over billions of years. When light from those systems reaches us, it shows their past selves. The universe in earlier stages, frozen across vast distances and time. Some of those images reveal elegant spirals with bright centers. Others show elliptical swarms shaped by collisions and gravitational tides. Every photograph of a faraway galaxy is both evidence and memory, a quiet record of creation unfolding beyond our reach. Between those galaxies lies more space than light could cross quickly, silent regions that stretch as the universe expands into greater emptiness. This void is not truly empty, but filled with faint radiation and dust. Small remnants of events scattered since the beginning. Even the dark voids tell stories through subtle gravitational pull, unseen bridges connecting distant clusters through invisible threads. When mapped together, these paths create the cosmic web, a hidden architecture that shapes everything else we observe. Globular clusters are ancient spheres of stars orbiting galaxies. Tightly packed populations hold hundreds of thousands of suns in a compact volume. Their stars are old and metal-poor, relics of early times. Their ages provide limits on how long galaxies have been assembling. Because they orbit halos rather than disks, they trace broad paths. Their motions preserve clues to long-forgotten mergers. To gaze upon a cluster is to see endurance, a shared history, bound by gravity and time. Some clusters contain stars with unusual compositions. Subtle variations reveal multiple generations, born from recycled gas. These layered histories make each cluster unique, their patterns revealing how galaxies evolved through countless eras. Astronomers use these differences to measure the age of the Milky Way, tracing how smaller systems merged into larger ones. The longer we study these spheres, the deeper the timeline becomes, stretching back to the dawn of star formation. At the center of our galaxy lies Sagittarius A, a supermassive black hole. Its immense gravity binds the Milky Way together in silent control. Around it, millions of stars orbit at breathtaking speeds, their motion revealing the hole's enormous hidden weight. We cannot see the hole directly, but its influence is visible, shaping the orbits of everything within the galactic core. It reminds us that even invisible things can define the structure of an entire galaxy. Occasionally, that black hole flares with bursts of radiation, energy released as gas falls inward and heats near light speed. Telescopes capture these flashes, brief but powerful, a way to study the physics of extreme gravity without direct sight. Each event reveals how matter behaves when trapped by space-time, confirming theories once only drawn on paper. Through these observations, the mystery feels closer, as if we glimpse the heart of the universe, itself breathing. Further outward, enormous jets of plasma rise from active galaxies, twin streams racing outward for thousands of light years. They mark where black holes consume and regulate cosmic energy. These structures are so vast they span multiple galaxies, their visible glow extending far beyond stellar neighborhoods. Through them, we see that energy and matter interact on scales far beyond comprehension. The radio signals from those jets travel across deep time, each pulse carrying details about motion, speed, and direction. By measuring them, astronomers map invisible magnetic fields. Such discoveries remind us that the universe is never truly quiet, but filled with faint conversations between matter and energy. Nearby, smaller galaxies orbit the Milky Way like satellites. These companions are ancient survivors of cosmic assembly. Each one carries unique signatures of chemical history, their stars preserving the record of past collisions. As they pass close, gravitational tides strip away stars and gas, forming extended streams that weave through our sky. They tell the story of how the Milky Way grew, gathering new members across billions of years. One such companion, the Sagittarius dwarf, is slowly dissolving, its stars forming a ribbon across the galactic halo. This ongoing process shows that creation and loss coexist. Galaxies are never static. They change like living organisms. Even our home system is shaped by the remnants of those past encounters. Farther away, colliding galaxies show us the drama of transformation. Their arms twist, stars scatter, and new generations ignite. Although chaotic, the process is not destructive but creative, forging structures that will endure long after the collision ends. As dust clouds compress under pressure, fresh stars are born. In every violent event, nature continues its patient cycle of renewal. Over time, such mergers build massive elliptical galaxies, bright cities of stars with smooth outer curves. Unlike spirals, they have little gas for new formation. Their populations grow old and fade slowly. These galaxies shine with red light from ancient suns, reminders of how the universe ages gracefully. From them we learn that cosmic beauty changes, trading youthful brightness for quiet maturity. Quasars are among the brightest objects ever observed. Their light surpasses entire galaxies combined. They are powered by feeding black holes at their cores. The infalling gas releases tremendous energy. Quasars allow us to study the distant universe, their signals showing how matter behaved in ancient epochs. To witness one is to peer into cosmic childhood, where the first great engines of light were born. Some quasars are so distant that their photons began traveling when the universe was only a fraction of its current age. Each detected particle carries that long memory, moving unbroken through the void. By comparing these signals, scientists measure expansion and structure. Through quasars, the universe speaks softly of its beginnings, and the faint echo still reaches us today. Stars themselves are nuclear furnaces burning hydrogen to helium. Their energy supports layers that would otherwise collapse. Every second, countless reactions forge elements in steady balance. When fuel runs low, the process changes, creating heavier atoms. These steps define how stars live, evolve, and die. Massive stars end their lives in supernova explosions, bright bursts that briefly outshine entire galaxies. Such events scatter the building blocks of life across space. Their remnants form neutron stars or even black holes, compact cores left behind after cosmic fire. In their destruction lies the source of creation, an endless cycle of renewal written in light. The quiet stars, like our sun, follow gentler endings, shedding outer layers to form glowing planetary nebulae. Their remains drift outward in colourful shells, while the inner core cools into a white dwarf. Even in fading, these suns enrich their surroundings with new materials. From their dust, future worlds might eventually emerge, continuing the chain of existence. Beyond all this, there are rogue planets moving through darkness, free worlds not bound to any star. They travel silently across interstellar space, their frozen surfaces untouched for eternity. Some may once have belonged to systems and were cast out. Others were born alone, forming as failed stars in isolation. The universe is not scattered randomly, but shaped by hidden threads. Faint filaments of matter stretch across cosmic distances, binding galaxies together in delicate structure. This vast web forms the framework of everything we observe. Invisible lines of gravity and dark matter guiding where stars and clusters grow. Even in emptiness, there is order and pattern, each region connected through subtle pulls across unimaginable spans. To look at the large-scale map of the cosmos is to see design without intention, only physics shaping art. When computer simulations model the universe, they show a similar lattice, long filaments separating empty voids, weaving an intricate skeleton of light and darkness. These patterns match what telescopes see across deep fields. It means the universe builds itself naturally from tiny differences, as gravity pulls, shaping matter into the forms we see today. The result is both simple and immense, a balance between chaos and cosmic organization. At the intersections of those filaments lie clusters of galaxies, each one a crowded realm of billions of stars. Gravity gathers them into vast cities that orbit shared centers, and within these, galaxies collide and merge like drifting continents. Hot gas fills the spaces between them, glowing faintly in X-rays. Astronomers study that light to trace how matter moves, revealing the slow evolution of the cosmic web itself. Between the clusters are enormous voids where matter is scarce. These regions span hundreds of millions of light years and remain mostly empty. Though silent, they define the scale of the cosmic pattern, surrounding filaments with wide gaps of stillness. Inside them, only a few lonely galaxies drift, cut off from the denser chains. These voids remind us that absence has its own form, sculpting contrast against the crowded parts of the universe. In the web's structure, dark matter plays the leading role. Though unseen, it holds 5 times more mass than visible material. Its presence is known only through how it bends light, a quiet influence that maps itself through gravitational lensing. Without dark matter, galaxies could not stay together. Their stars would drift apart, their disks unraveling over time. Thus, the unseen component defines the visible shape of everything. Scientists use gravitational lensing to reveal these hidden paths. When light passes near massive structures, it curves, forming distorted images. Through these arcs, astronomers reconstruct the mass that cannot be seen. Each lensed image becomes a clue to the invisible framework. This technique allows us to study the dark side of creation, turning invisible forces into visible maps of influence. Some lenses magnify distant galaxies that would otherwise be lost, a natural telescope created by the universe itself. This magnification lets us glimpse the earliest structures of cosmic formation. Each discovery adds another point to the web, connecting old light with new understanding. It's like finding threads in a vast, unseen tapestry, every strand contributing to the grand cosmic picture. On the grandest scales, galaxies move not randomly, but within these filaments. Their motion reveals the tug of gravity stretching across billions of light years. This motion defines the cosmic flow, a slow migration of matter. Even now, the Milky Way is traveling toward a distant gravitational center. We are part of that motion without feeling it. Passengers on a drifting raft carried by universal currents. The Great Attractor is one such gravitational region, pulling thousands of galaxies toward its dense heart. It lies hidden behind the Milky Way's dust, a mystery still not fully mapped. Beyond it lies the Laniakea supercluster, our local cosmic home, a vast basin of space containing over 100,000 galaxies. Its name means immeasurable heaven, fitting for its sheer scale. Each galaxy moves along gravitational streams, converging like rivers into the center. Within that motion, we can trace our place, a single dot within a boundless family of light. The Milky Way itself is moving within that larger structure, spinning while drifting toward the neighboring Andromeda galaxy. In billions of years, the two will merge, forming one massive system. This is a normal fate for galaxies, part of cosmic evolution. Their stars will not collide but pass, rearranging into a new elliptical form. If we could speed up cosmic time, we'd see the web pulse and shift, galaxies moving along filaments like streams of light. Clusters grow as smaller systems fall into them. The voids expand, stretching ever wider with cosmic expansion. This constant motion forms the rhythm of existence, the universe breathing slowly on incomprehensible scales. Astronomers simulate this process using supercomputers. Their models show how dark matter determines where galaxies form. These visualizations resemble vast nerves spreading through darkness. It is humbling to see how complexity emerges from simplicity. What began as tiny fluctuations in density became the entire cosmic web. The web itself glows faintly with hydrogen light. Telescopes detect it through careful mapping at specific wavelengths. This emission comes from filaments warmed by nearby galaxies. It proves that the space between is not empty, but alive with motion. Each faint photon reveals how deeply connected the cosmos truly is. Some filaments stretch millions of light years between major clusters, narrow bridges carrying gas and matter. As galaxies move, they draw fuel from these paths. The process keeps cosmic evolution continuous and smooth. Without them, star formation would fade earlier across the universe. When we look farther into space, we look back in time. Light from distant structures shows the web's youth. The filaments then were thinner, the clusters smaller, and voids less defined. Over eons, gravity thickened the threads, weaving complexity into the fabric. The web is a record of the universe maturing, growing denser and more connected with every passing age. Dark energy also shapes the fate of this web, accelerating expansion so that filaments drift farther apart. Eventually, galaxies will no longer see one another's light. The universe will appear more empty, though nothing has truly ended. Only the bridges between clusters will have stretched beyond reach. The cosmic microwave background still fills the void. The last glow of the early universe spread evenly across the sky. It is faint, ancient, and almost uniform. Embedded within it are tiny variations that seeded the web itself. Those ripples became the scaffolding of galaxies and all structure. From our position, the universe seems static, but every second changes. Stars die, galaxies merge, and filaments realign their paths. The motion is too vast for any human eye to perceive. But when we measure, when we record, we see growth. The web continues to evolve silently, without pause or end. Some galaxies in the web emit strong radio waves, signals of energetic cores filled with activity. Others lie dormant, quiet for billions of years, doing little but drift. The variety makes the cosmic landscape endlessly fascinating. Every light and silence contributes, balancing energy across the endless depths. Astronomers sometimes say we live in a lucky time because we can still see the structure before it fades. In trillions of years, expansion will erase this view entirely. Our descendants, if they exist, will believe their galaxy is all that remains. We are witnesses to a universe still young, and that knowledge makes each discovery quietly precious. Even now, new instruments refine these measurements, mapping filaments, voids, and clusters with higher precision. The cosmic cartographers of our age chart regions never seen before. They measure motions invisible to the naked eye. Each new result confirms that order underlies even the darkest regions. What holds the web together is simple gravity, the same force keeping your feet on the ground. It acts across scales from atoms to galaxies. Though weak individually, its reach is infinite. That same pull weaves together the universe's fabric from beginning to end. If you were drifting through space between those filaments of light, the silence would be deeper than imagination. You might pass through invisible currents of hydrogen gas, faint but real. Galaxies would appear as glowing islands, far on the horizon. In that stillness, you would sense the vastness of cosmic connection. Every image of the web reveals how the universe organizes, not by plan, but through gravity's slow conversation. Each structure affects another, across immense distances. It's a universe of relationships rather than objects. and we too are participants, atoms from one small thread in the whole. In the end, the cosmic web is both map and mirror, showing where we come from and what holds us together. The light from distant galaxies tells us how it all began. Each discovery deepens that quiet understanding, and through that knowledge, we find our place, suspended gently within the endless network of the cosmos. The stars we see at night carry ancient stories. Their light travels across billions of years before it finally touches the stillness of our world. Each glowing point above our heads is a distant sun, burning quietly, repeating the same fusion that powers everything we know. Their brightness varies depending on distance and mass. Some appear faint only because of the immense void between us and them. To gaze upward is to look backward through time, seeing the past as it once was, frozen in traveling light. Those stars are never truly still but in constant motion, orbiting the Milky Way's center through a sea of gravitational balance. Even our sun joins that endless journey, circling once every 200 million years without us ever feeling the motion. Each turn rewrites our cosmic address while keeping our home inside a stable spiral arm of starlight. Across those orbits, gravity maintains order, its steady pull guiding billions of suns without error or noise. Inside vast clouds of hydrogen, new suns form. Gravity draws gas inward until heat and pressure awaken nuclear fire. These nurseries glow with soft infrared emissions, invisible to our eyes, yet rich with the beginnings of life and energy. Every particle joins another through delicate forces, slow collisions building complexity atom by atom. What begins as chaos becomes structure, a balanced pattern repeated throughout every galaxy ever born. Around those newborn stars, disks of matter spin. Fine dust and rock gather into worlds under gentle, constant motion. Each collision adds to the growing mass, shaping planets, moons, and frozen bodies farther away. When the gas clears, the system stabilizes, leaving behind orbits that will last for billions of silent years. It is in those disks that possibility appears, the slow progress from dust to solid ground, from chance to order. Massive stars burn furiously and die in violent supernovae. Explosions bright enough to outshine galaxies for a brief, dazzling moment. Those blasts create heavier elements, scattering carbon, oxygen, and iron into the surrounding interstellar sea. From their remains, new generations of suns are born, inheriting the raw material for planets and life. Destruction is never final in this process. Every ending feeds the next beginning with quiet purpose. Smaller stars fade peacefully into white dwarfs, shedding outer layers that glow like shells of soft color. Their cooling cores remain for eternity, radiating faint heat long after their energy has dimmed. Such endings reveal the universe's calm logic, showing that not all transitions must end in violence. Each quiet death is a reminder that balance, not brilliance, sustains cosmic continuity. Some systems contain two suns locked in shared orbits, trading matter across invisible bridges of gravity. When one expands into a red giant, gas flows toward its smaller companion, forming luminous disks of plasma. Those streams create recurring flashes of nova light, brief messages written across the darkness of space. Through such exchanges, we learn how gravity and fusion interact, shaping not just stars, but the rhythm of renewal. When two dense objects collide, space-time shakes, releasing gravitational waves that travel untouched through the cosmos. Each ripple carries information, proving that even void can bend and move like water under unseen pressure. Detectors on Earth have heard these silent vibrations, confirming predictions made a century ago. They remind us that the universe is not rigid, but responsive, alive in ways our senses can barely comprehend. Our Milky Way has many faint companions, small galaxies orbiting within its wide gravitational field. Some are ghost-like clusters of ancient stars, their faint shimmer barely visible against the deep backdrop. They record the earliest eras of formation, preserving the first generations of suns ever created. Each orbit tells a story of interaction, slow merging and mixing that continue to shape our home. When galaxies approach, their gravity stretches matter into luminous bridges, long trails of gas and stars linking them together. These streams glow under ultraviolet light, tracing collisions that last millions of years. The process seems chaotic, but remains predictable, guided entirely by the same laws that move a falling stone. From these encounters, new shapes are sculpted, spirals and rings marking the choreography of cosmic evolution. Far beyond, galaxies form immense webs of filaments and voids, connected by dark matter we cannot see directly. Each filament extends for millions of light years, a glowing thread woven through expanding space. Between them, near-empty regions stretch vast and silent, containing only a few scattered systems adrift. This pattern reveals the deep architecture of the cosmos, its grand design shaped by gravity's timeless pull. The redshift of faraway galaxies shows universal expansion, space itself stretching rather than objects moving through it. As light travels, its wavelength lengthens, sliding toward the red end of the spectrum. This shift proves that everything once stood closer. The cosmos still carries the momentum of its own beginning. Through these measures, we chart the pace of creation, reading the pulse of time across the largest possible scales. Among the brightest objects are quasars, powered by enormous black holes, drawing matter inward until it releases torrents of energy. Their jets of plasma extend for light years, visible across the universe's depths. These signals guide astronomers toward ancient epochs, showing what galaxies were like when they first began. Each quasar is both a window and a mirror, revealing the extreme limits of known physics. Cosmic rays move through all space like invisible rain, subatomic particles crossing galaxies at nearly light speed. They strike our atmosphere with quiet regularity, proof that even emptiness is filled with motion and exchange. Most pass through without impact, leaving only faint traces in instruments. Their existence reminds us of hidden activity, the constant unseen conversation between energy and matter. The interstellar medium is more than simple emptiness. It is a thin soup of dust and gas stretching between stars. Every photon that passes through it is slightly altered, its color shifted by scattering and absorption. That gentle filtering tints distant starlight redder as it travels, a record of every collision along its path. Through this subtle haze, we perceive the depth of space, a quiet evidence that even the void has structure. When we analyze stellar spectra, familiar elements appear: carbon, oxygen, iron, the same found within our bodies. Each atom of blood and bone was once forged inside a star, scattered and recycled through generations of explosions. To exist is to carry starlight within our cells, a physical connection linking us to the oldest fires of creation. In that truth lies quiet comfort, the knowledge that we are made of the same matter as the universe itself. The expansion of the universe continues without pause, each moment of time stretching the fabric of space a little farther than before. Every galaxy moves away from every other, not through motion in space, but through space itself growing in size. The farther a galaxy lies, the faster it recedes. Its light red-shifted into longer wavelengths that carry echoes of ancient beginnings. This ongoing stretching is the quiet rhythm of existence, a cosmic heartbeat that has lasted for almost 14 billion years. Dark energy drives this acceleration with unseen force, its nature still hidden from both observation and experiment. It fills all regions evenly, acting as uniform pressure that counteracts the pull of gravity. Scientists measure its influence through the faint light of distant supernovae, watching those explosions drift farther than expected. The results show that dark energy grows stronger over time, an invisible agent guiding the future toward faster expansion. If expansion continues, galaxies will separate beyond all communication, their signals stretched until even light cannot bridge the distance. In billions of years, observers in far futures may see only their local cluster of stars. The rest of the universe will fade from visible reach, its light diluted into wavelengths too long for any instrument to detect. Cosmologists call this the isolation era, a silent epoch where each surviving island drifts alone through emptiness. The temperature of space keeps falling with this expansion, its faint background cooling by small degrees every 100 million years. That background is the afterglow of creation itself, the ancient radiation left when matter and energy first decoupled. As wavelengths stretch, the glow dims further into radio frequencies. Eventually, even that whisper will fade below all detection, leaving the cosmos nearly black to every possible eye. Long before that happens, our own galaxy will change, drawn toward the neighboring Andromeda by mutual gravity. Despite expansion, local forces dominate where matter is dense enough. In about 4 billion years, the two galaxies will collide and merge, forming one larger spiral or elliptical structure. Stars will rarely strike each other directly, yet their motions will shift dramatically as gravity finds a new balance. Such mergers create bursts of star formation, gas clouds compressing under sudden gravitational pressure. The night skies of future worlds may shine brighter with newborn clusters. Central black holes will combine, releasing gravitational waves, subtle ripples spreading quietly through space-time. From these collisions, new patterns emerge, proof that even destruction can lead to renewed order. Beyond visible galaxies, the cosmic web extends. Filaments of matter linking clusters across hundreds of millions of light-years. At their intersections lie massive nodes, places where gravity has sculpted the largest structures ever known. Dark matter binds these strands together with steady pull. Through mapping their distribution, astronomers reveal the hidden framework of the universe. Simulations on supercomputers recreate this growth. starting from the slight ripples in density after the Big Bang. As time advances, those ripples amplify, pulling material into complex networks. Every filament in those models mirrors reality closely, a visible echo of invisible mathematics. By comparing them, we refine our understanding of gravity, adjusting how energy and matter interact across vast distances. Closer to home, our solar system follows predictable paths, each planet orbiting under the Sun's ancient authority. Gravitational interactions slowly alter those paths, trading momentum and reshaping distances over eons. Even stable systems change slightly, a continuous process of balancing. No orbit is perfectly fixed, yet all remain faithful to the laws that began them. As the Sun ages, it will brighten gradually, increasing its luminosity and altering Earth's fragile climate. In roughly 1 billion years, the oceans may evaporate, leaving behind dry continents under relentless heat. Life as we know it will adapt or fade, shifting toward extremes of survival as conditions grow harsh. Eventually, the Sun will become a red giant, expanding outward until its outer layers swallow the inner planets. When the Sun's fuel runs low, fusion ceases. Gravity will pull its core inward, creating a dense white dwarf. Its remaining heat will slowly leak into space, a process so gradual it lasts for trillions of years. That remnant will mark the final phase of our solar family. Long after Earth is gone, its atoms will drift through space, recycled into new forms elsewhere. The life cycle of stars and galaxies echoes the universe's own pattern, continual renewal through collapse and creation. Everything follows the same rules of conservation and energy. What ends in one place begins in another. This repeating balance maintains harmony, ensuring the cosmos neither stagnates nor truly dies. Scientists measure cosmic time through light's travel. Every photon acts as both messenger and witness of distant events. Observing them reveals how far into the past we are looking. Light from the earliest galaxies still arrives now, bridging 13 billion years of expansion. Each beam is a record of conditions long gone, a surviving thread connecting origin to present. As instruments improve, the observable edge shifts. Telescopes like JWST capture infrared light too faint for older eyes. These images show galaxies in their infancy, small clumps merging to become the spirals we recognize today. Through them, we witness cosmic history unfolding, an evolving film projected across blackness. Each discovery brings both answers and new questions, expanding wonder faster than certainty. Beyond light, neutrinos flow endlessly through matter, ghost-like particles that rarely interact with anything at all. Trillions pass through your body every second without trace. They carry information about the cause of stars and explosions invisible to photons. Studying them lets us hear the universe through silence, turning absence into measurable presence. Even the fabric of space-time vibrates with subtle waves, gravitational ripples spreading from collisions of massive bodies. These distortions stretch and squeeze all dimensions, passing through planets without resistance. Detecting them demands impossible precision. Lasers measuring distances smaller than atomic widths. Every confirmed wave is a voice from deep time, a clear signal proving Einstein's predictions endure. Dark matter remains one of the great mysteries, its presence inferred only through gravitational influence on visible objects. It outweighs normal matter by nearly 6 to 1. Without it, galaxies would fly apart, their stars lacking the unseen mass that holds them together. Scientists build sensitive detectors underground, waiting for even a single particle to reveal itself. If found, it could change physics profoundly, unlocking deeper laws behind symmetry and stability. The search continues with quiet patience. Experiments across continents working in concert. Each failure narrows the range of possibility. On the scale of trillions of years, entropy rules, energy spreads, temperature evens, and usable work declines. Stars fade into remnants, black holes evaporate through Hawking radiation. The universe grows colder, emptier, yet remains structured. Even in that distant future, motion and decay persist, proving that stillness is an illusion of limited time. Eventually, only degenerate matter will remain. White dwarfs cooling into black dwarfs, invisible to any eye. Protons may decay, atoms vanish, leaving pure energy behind. At that horizon of existence, physical laws may transform, guiding the next iteration of reality. Some theories suggest a new birth may follow, the universe expanding again from quiet vacuum. If such rebirth occurs, time itself will reset. Every trace of our present era erased, yet echoed in structure. The next cosmos could inherit our constants, its laws shaped by statistical memory of the last. Creation might not be a single event, but an infinite cycle. To imagine that pattern is to sense continuity, a comforting idea that existence never truly ends. Through all of this, humanity observes from one small world, a fragile vantage surrounded by distances beyond comprehension. We build instruments to extend our sight, to hear faint whispers of the unknown. Our curiosity drives us across decades and discoveries, linking countless minds through shared wonder. Each insight adds to a quiet legacy, proof that awareness itself is part of the universe's story. Even now, as you listen, these same truths flow through you. Each word a reflection of cosmic history passing through thought. Every particle inside you once belonged to ancient stars, scattered, cooled, and reassembled into your living form. You are not separate from the vast whole, but its conscious fragment. So breathe softly, let that truth settle, and rest within the continuum that connects all matter and all time. Astronomers once believed the Milky Way was the entire universe. It took centuries of observation before distant spirals were understood as separate galaxies. Those faint smudges in early telescopes appeared small and hazy, yet each contained billions of stars arranged in graceful rotation. When Edwin Hubble measured their distances, the numbers exceeded all expectation. His results showed that the Milky Way was just one member of a much larger collection. From that discovery, cosmic perspective changed forever. Humanity realized its position was not central, but peripheral among countless others. Every deep sky image since confirms this truth. The night sky holds more galaxies than grains of sand on Earth's beaches. Each is unique in color, shape, and stellar content. Together they form the visible skeleton of the universe, a map traced by gravity's endless influence. Within those galaxies, black holes sit at the centers, silent cores where matter collapses beyond all known limits. Their gravity is so intense that not even light can escape. Surrounding gas forms glowing disks, heating to millions of degrees as it spirals inward under relentless pull. When those disks flare, they outshine entire galaxies, marking the heartbeats of invisible monsters. Supermassive versions reach billions of solar masses, shaping their environments through jets and radiation. They regulate growth by limiting new star formation, turning cosmic neighborhoods into quiet zones. Astronomers monitor these engines using X-ray and radio signals. Their activity explains why some galaxies blaze while others rest. Not all extremes are large. Neutron stars compress incredible density. A teaspoon of their matter would outweigh a mountain. These remnants spin rapidly after supernova collapse, releasing radio beams like cosmic lighthouses. We call them pulsars because their light pulses with perfect regularity. Their precision rivals atomic clocks, allowing scientists to measure gravitational waves across interstellar distances. The magnetic fields of these objects reach unimaginable strength, twisting space near their poles. Sometimes they release short bursts of gamma radiation, flashes visible across the universe. Each event marks a sudden rearrangement of intense magnetic forces. Though brief, those moments reveal physics that cannot be recreated on Earth. Insight from the cosmos itself shared. Between the stars floats interstellar dust and thin gas, seemingly empty yet filled with complex chemistry. Atoms collide, bond, and form molecules that become the seeds of life. Spectroscopy shows traces of alcohols, amino acids, and even sugars, drifting freely across dark clouds. Every ingredient for biology already exists among the stars, waiting for the next world to assemble. In these clouds, new suns are born. Gravity gathers material into dense cores. As they heat, fusion ignites, and starlight begins its long journey. The leftover gas forms disks that may create planets over time. Within those swirling regions, small rocks stick together, building the foundation of future systems. Our own planetary neighborhood emerged from such a disk, the Sun capturing debris 4.5 billion years ago. Each planet took shape through countless collisions, merging fragments into stable worlds. Jupiter's immense gravity influenced everything, shielding Earth from some impacts while scattering asteroids outward. Without that protection, life here might never have survived, one planet's bulk preserving another's chance to exist. Earth's magnetic field guards against solar winds, deflecting charged particles that would strip our atmosphere. Generated by motion in its molten core, the field extends far into space. Auroras near the poles display its strength, shimmering curtains created by trapped electrons colliding with air. Those lights remind us that invisible forces shape even the quietest skies. The moon, our steady companion, controls tides through subtle gravity, pulling the oceans back and forth in endless rhythm. Its surface preserves a record of impacts billions of years old. Without the moon, Earth's axial tilt would wander chaotically, making climates far less stable for life. The lunar bond anchors our planet's wobble, a cosmic partnership written in motion. Beyond our system lie exoplanets in astounding variety, some large and hot, others frozen or cloud-covered. Many orbit red dwarfs, their short distances creating temperate zones close to faint stars. Astronomers find them by watching shadows cross starlight, each dip revealing size and orbit. These discoveries show that planetary systems are common, perhaps countless across the galaxy. Some of those worlds rain molten glass sideways, others endure metallic snow that falls and vaporizes. There are planets with iron clouds and ones with diamond storms. Weather there defies human comparison. Yet each phenomenon follows physical laws. Studying them deepens our sense of planetary possibility, broadening what habitable can mean. One especially strange world, nicknamed HD 1T9733b, glows deep blue, its color caused by silicate particles scattering light. Winds there reach thousands of kilometers per hour, flinging glass shards sideways through superheated air. No ocean lies beneath that color, only vaporized minerals forming stormy haze. It is both beautiful and terrifying, a reminder that alien skies may glitter with danger. Another, called 55 Cancri E, might contain thick layers of carbon, compressed into diamond deep within its mantle. Temperatures on its surface exceed 2,000 degrees, making even the hardest minerals glow faintly. Such extremes reveal how chemistry adapts beyond our familiar norms. To imagine diamond rain falling endlessly there is to sense how extravagant creation can be. Back in our galaxy, stars orbit in distinct populations, some older, some freshly formed. They trace spiral arms defined by density waves, regions where clouds compress and ignite. The sun passes through these zones every few 100 million years. Each crossing influences the inflow of comets, dust, and cosmic rays, shaping subtle cycles of planetary climate. Cosmic rays themselves are particles accelerated to near-light speed, born from violent events like supernovae. When they strike Earth's atmosphere, they split atoms and create showers of secondary fragments. Though invisible, they affect electronics and even mutation rates in biology. They remind us that space touches life continuously, not through visits, but through constant unseen contact. Supernovae, the deaths of massive stars, spread heavy elements everywhere, forging calcium, iron, and gold in seconds. Each explosion seeds interstellar clouds with fresh materials. Without such deaths, planets could never exist. The gold in your jewelry once shined inside a dying star, proof that beauty arises from cosmic violence. The rate of supernovae across the universe varies with star formation, bursts of birth and death rising together. Galaxies undergoing mergers show higher frequency. Astronomers track them through infrared and X-ray afterglows. Each event becomes another marker of cosmic time, a flash whose light tells stories billions of years old. Between galaxies lies tenuous plasma called the intergalactic medium. It holds most of the universe's ordinary matter. This material remains too thin to emit much light, yet it connects clusters into vast filaments. By observing quasar spectra, scientists detect absorption lines from that gas. Those lines trace the invisible web stretching through space, the infrastructure behind all structure we can see. Quasars themselves are brilliant beacons powered by supermassive black holes. As matter falls inward, it heats and radiates with staggering luminosity. They serve as cosmic lighthouses, visible across enormous distances. Looking at one is like peering back in time, witnessing the early universe still forming. Their light reveals chemical composition of intervening gas, showing how elements built up over cosmic history. Even the pattern of that light's shift records the rate of universal expansion. Thus, each quasar doubles as a natural experiment. From them, we refine our constants, using observation to guide theoretical understanding. Not every cosmic object emits light directly. Some reveal themselves only through motion. Gravitational lensing bends light from more distant sources. When a massive cluster aligns with background galaxies, arcs and rings appear. These distortions allow us to weigh invisible matter, transforming geometry into cosmic scale. Lensing confirms that most mass is unseen, yet its effects sculpt every observed map of the sky. It also magnifies otherwise unreachable objects. Thanks to this bending, we glimpse galaxies from just a few 100 million years after the Big Bang. Thus, gravity becomes both artist and telescope, shaping vision while extending reach. Through all these layers of discovery, a quiet pattern repeats, curiosity leading to deeper calm. Each revelation, no matter how grand, returns to the same point, our wish to understand. Knowledge itself feels like a form of light, spreading gently into dark corners of ignorance. And as we learn, the universe learns itself through us, awareness folded back into creation. Astronomers have measured the faint afterglow of creation called the cosmic microwave background. It is the oldest light we can ever see. This radiation fills all of space, stretched to radio wavelengths by the expansion of time itself. Tiny fluctuations within it record the earliest clumps of matter. They later grew into galaxies and clusters. Looking at that map is like reading the baby picture of the universe. The temperature of that glow is just 2.7 Kelvin above absolute zero. Yet it contains endless information. Each subtle variation marks regions of density that guided cosmic structure. Decades of study have refined our understanding of age, curvature, and cosmic balance. It is the faint echo of the beginning, humming through every direction of the sky. Dark matter remains one of the universe's most persistent mysteries. It outweighs visible matter 5-1, yet refuses to shine. We infer its existence only through gravity, watching how galaxies rotate. Without it, stars at the edges would drift away, unable to remain bound to their galactic homes. It forms halos around galaxies, shaping their motion and interaction. Dark energy is even more enigmatic, driving the accelerating expansion of the cosmos. Its nature remains unknown, possibly a property of space itself. Observations of distant supernovae revealed this acceleration, altering our entire view of cosmic fate. Instead of slowing down, the universe speeds up, stretching faster with each passing epoch. Some scientists propose that this expansion may continue forever, leading to a lonely future of darkness. Galaxies will drift beyond visibility, their light too faint to reach anyone. Eventually, even stars will fade into cold remnants. White dwarfs and black holes, the cosmos will enter its long night, vast, still, yet filled with memory. Others wonder if gravity might someday reverse the trend, pulling matter back together. That would end in a big crunch, a collapse returning all energy to a single point. Perhaps the process would begin again, another big bang following silence. If so, the universe could cycle endlessly, rebirth following cosmic rest. Closer to home, the sun will one day expand into a red giant, consuming Mercury and Venus before cooling to a dwarf. This will happen 5 billion years from now, long after humanity as we know it has changed. The remaining core will glow softly for trillions of years. Its light will fade slowly, leaving behind carbon and oxygen, the future dust of new worlds. Even before that distant fate, solar winds constantly reshape our environment, a stream of charged particles sweeping through interplanetary space. This wind interacts with magnetic fields of planets, creating auroras where it collides with air. Its pressure forms the outer boundary of our heliosphere, a bubble shielding us from galactic radiation. When that bubble eventually shrinks, other stars' winds will touch ours. Beyond the solar system lies the Oort cloud, a vast sphere of icy bodies orbiting far beyond Pluto. It contains billions of comets, leftovers from formation's earliest days. Occasionally, gravitational nudges send them inward towards sunlight. Their long tails reveal ancient material preserved for billions of years. When a comet passes close to the sun, its ice vaporizes into bright plasma, releasing trails of dust behind. That dust sometimes crosses Earth's path, giving rise to annual meteor showers. Each streak you see in the night sky is a tiny grain burning high above the atmosphere. They are small reminders of cosmic debris still visiting their origin star. Farther still, interstellar objects occasionally enter our system, like Oumuamua and 2I Borisov. They move on hyperbolic paths, never bound to the sun. Their unusual shapes and compositions reveal new physics of distant regions. Each one is a wandering messenger, a piece of another solar birthplace. Within the Milky Way, the rotation of stars follows an intricate pattern. Our sun completes one orbit every 230 million years. It carries Earth through changing environments, from dense clouds to open voids. This motion subtly affects cosmic radiation reaching our planet. We are passengers on a vast ship, crossing oceans of interstellar space. At the heart of our galaxy lies Sagittarius A, a supermassive black hole, about 4 million times the mass of the Sun. It sits quietly most of the time, feeding rarely on nearby gas. When it does, the flare brightens the galactic center. This quiet hunger reminds us that power can exist without constant display. Other galaxies contain even larger beasts, some with 10 billion solar masses. When those holes accrete gas, their energy output exceeds that of entire galaxies. These quasars blaze across the early universe, visible from incredible distances. Their light acts as a beacon, marking both danger and discovery. Between galaxies, immense voids span millions of light years, regions where matter is sparse and silence absolute. Yet even there, faint whispers of radiation flow, Cosmic filaments connect those empty spaces together, like threads of an invisible web. They bind clusters into the universe's overall architecture. The largest of these clusters, the Virgo supercluster, contains our own Milky Way, along with thousands of others. Within it lies the Laniakea region, meaning immense heaven in Hawaiian. This is our true address in the cosmos, a structure 500 million light-years wide. It moves together as a gravitational continent, drifting slowly through space's dark sea. Zoom out further and you see even grander patterns, superclusters arranged in filaments wrapping around cosmic voids. This large-scale structure resembles a neural network, filaments glowing like cosmic synapses. Some scientists note the eerie similarity between the universe and the brain. Perhaps structure repeats at every scale, consciousness written into the pattern of matter. Back on Earth, every atom in your body was once part of a star, forged in supernovae long before the sun was born. The calcium in your bones, the iron in your blood, all recycled cosmic dust. You are literally a product of stellar death. To exist is to be connected, not metaphorically, but by atomic heritage. Every breath you take contains ancient particles of oxygen, some once bound within a comet or drifting in interstellar gas. The air mixes histories across ages, cosmic material passing through generations of life. To breathe is to participate in creation, a quiet exchange between star and self. Even sleep becomes a part of that cycle, rest echoing the universe's own rhythm. Looking up at the night sky, you witness light that has traveled for eons. The stars we see are frozen in time, their true states changed long ago. Our vision is always past-oriented, never present. Every photon a time traveler. To gaze upward is to remember, to share awareness with the ancient cosmos. In some distant future, galaxies beyond our local group will vanish from view, their light receding faster than time allows. Only a few will remain visible, clustered around gravity's hold. Future astronomers might see a sky almost empty. They would never know how vast the universe once was. Yet knowledge leaves durable traces, records stored in data, memory, and human curiosity. Even when galaxies fade, our understanding may persist. Every theory, every observation extends awareness beyond the fragile moment. To seek truth is itself a form of survival, the cosmos learning through us. The idea that space and time are connected comes from Einstein's relativity, showing that gravity is geometry rather than force. Mass bends space-time, altering motion for all that passes near it. This realization changed both science and imagination, revealing that even emptiness can curve. The next great insight may await another quiet thinker. Quantum mechanics, by contrast, reveals the smallest scale, where uncertainty defines every event. Particles appear and disappear, connected through probabilities rather than paths. This behavior might also shape reality on cosmic levels. Perhaps the universe itself is a vast wave function, unfolding through infinite possibility. The more we learn, the more humility returns, for the unknown only deepens with discovery. We see farther, but not finished. Each answer multiplies questions across expanding horizons. This pattern keeps science alive, not as certainty, but as gentle curiosity. When we record distant signals, we collect whispers from the past, photons that began their journey before Earth formed. Telescopes act like time machines, translating faint light into meaning. Each spectrum tells a story: temperature, motion, composition, all woven into one trace. To decode them is to listen, as creation narrates its own history. Even silence in deep space is not empty. It hums faintly with virtual particles. Quantum fluctuations spark and fade, lending brief existence to ghostly energy. This vacuum energy might drive cosmic acceleration, subtle yet relentless in effect. Emptiness itself becomes an active participant, shaping the universe without touch. As we end this slow journey, take a quiet breath and feel how knowledge brings stillness rather than noise. Every fact you've heard tonight, every distant image or idea connects softly with the next. The universe remains patient, endlessly expanding, endlessly old. And in that awareness you may rest, your mind floating among stars while your body drifts towards sleep. Because this story will never truly end, the cosmos continues while we only pause. Each night sky is a reminder of that motion, calm, predictable, yet infinite. You are part of that same pattern, moving gently through time. So let go now, let your thoughts wander, and sleep in the rhythm of the universe.